Good morning. Thank you very much to be here. Some people is coming, I am checking because we are waiting people, but let me to introduce Concetto Spampinato. Is a good colleague that we are now collaborating with the people who are working in starting with European proposal, and also with collaboration with other colleagues from other university. Concetto is full professor, University of Catania, president of CIDIA and leader of the lab PeRCeiVe. As artificial intelligence lab serves, and he is, as I told you, the president of the Center for Informatics, Digitalization and Artificial Intelligence. He has high quality number of publications in different areas, like computer vision, foundation model, explainability, continual lifelong learning, and so on. Really, he has a deep and high quality curriculum and number of activities, and really it's an honor, a pleasure for us. He's acceptance to be here with a talk today about we will discuss in this case about explainability and understanding as our definition, but from the point of view of the vision models. And remember the question that I did introduce you about to open Catavenici in Nature published a paper 12 years ago with the question, the question of to open the black box, and then it is really we will enjoy with the talk of Concetto about this topic in the vision models. Thank you very much. Please.
Thank you everyone. Thanks for the invitation. I mean, I'm really happy to be here. I've been collaborating with the Granada people since a while, and now we finally meet in person. So today I'm gonna talk about opening the black box. So basically I will present you our recent works on how to understand and dissect the models by accessing both the model parameters and by using in an extremely black box way without accessing the model parameters. So what I will present is basically the activities that we do in our lab. So I created more than 10 years ago the PeRCeiVe lab. At the moment the lab has a few PhD students, several academic professors, and there are three main research groups. The first one is the cognitive inspired learning group, the medical and brain image analysis group, and the multimodal learning and reasoning group, where there is a sub-team on explainable AI. And here you see the people working on this area. So let's move directly to the talk. So this the agenda of this talk. I split the talk in 4 parts. The first one is foundations. I mean, I'll be presenting, but I'm sure you already know transformers and foundation models and how to adapt foundation models to downstream tasks. Then we will be talking about explainability and the one I called the explainability crisis. And then we will see the research we do on this topic. So from visual to text explanations, this is our recent work, and then how we move towards causal understanding. Okay, so let's start with the foundations. So we know that in the last, I would say, 5 years, there has been a trend moving towards task-specific models to general purpose models. So at least the not so young people like me, we started by doing feature engineering, then we moved to convolutional neural networks, where we basically learned features that were oriented to address a specific task. And now we are in the era where we have very general AI models, and we try to adapt these general models to specific downstream applications. So the story starts from transformers. So I guess you all know what a transformer is, but I decided to add these slides because we need to understand better how we use the transformer architecture to make our explainability approaches. So we know that in transformers we have this encoder-decoder architecture. And we know that everything starts from the source sequence, then we do some embedding, then this embedding goes through a set of encoders, a set of encoder layers where we basically learn let's say features at different abstraction level. And then in the original formulation there is also a decoder just to do some autoregressive task. And this architecture I was mentioning earlier. If we go deep and we look at the encoder architecture, we know that we have several layers, and these are the main, let's say, operations done within the encoder. So we have the multi-headed self-attention, and then followed by layer norm feed-forward network, and this goes to the next layer. The key intuition of transformer was the multi-headed self-attention, which also has strong implications on explainability, and we will see in a few minutes. And we know that in the self-attention, these the operations that we basically do, where we have key, query, and value, and we try to transform the input data into a new space. One important thing of transformers is basically that we do analysis on multiple heads. This is quite important because each single head at the end will learn some specific features on our data. So I assume you all know what the heads do. So basically, given the input feature, we just split down the features into multiple heads in a way just to understand what each single feature will represent. This is what basically it is done within the transformer. Given the value, where the value is the image, we just learn some attention weights, which comes from multiplying again the input by itself, and we obtain the output. When we do this at different heads, you can see in this slide that each single head at the end encodes some specific information from the input data. Okay, but I mean, this is just a very generic overview of transformers. We all know that transformers were born initially for text and for time series, but what I'm interested in, and because I was born as a computer vision scientist, the idea is the good thing is that transformer can be also applied to vision tasks. And this leads us to the VIT model. I guess you all know VIT, right? The VIT model, you know? Okay, in the VIT model, which is what was proposed in 2020, we treat image patches as a sequence. So we basically split down, divide the image into patches, and then each patch becomes a token in the sequence of transformer. In the case of VIT, we use only encoder. We do not use decoder because what we need to know is just to learn some more compact representation from images. Of course, since patches have 2 dimensions, they are flattened in VIT model. And this is the VIT architecture, where basically to do some specific, let's say, classification task. For instance, in the case of the paper, they just added one classification token. The classification token is the token that we basically use to make all our analysis. One of the main advantage of transformer was that transformer led us to the universal architecture. This was extremely important because this allowed the community to combine multimodal data and also data with arbitrary size. This was extremely, I keep saying to my students, this was the most important innovation of transformers, the possibility to have only one architecture for several tasks and for several different modalities. The consequence of this was that after transformer, we have the foundation models. I guess that we all know foundation models, and we know that the foundation model is a large-scale neural network, basically trained on large-scale data in an unsupervised way. Self-training, it is done for creating foundation models. And we know that at the end, foundation models just retain general knowledge. That knowledge needs to be adapted to specific downstream tasks. So yeah, there are 2 points. Generally, the good things is that for creating foundation models, we didn't need to have labeled data, and we used self-supervision. And these foundation models can be adapted to a wide range of downstream tasks. Okay? One of the most significant example, or one of the most important example of foundation models is CLIP, where we basically combine image and text, and we try to do a task which basically combine the two. So in the CLIP model, do you know CLIP, right? All of you? Okay. So in the CLIP model, we have one text encoder, transformer architecture, one image encoder, again, a transformer architecture. And these, of course, as text changes, image changes, we get several different embedding space. The idea of CLIP was to force encoders to have the same representation for the same concept. Okay, and this was trained using contrastive learning. So the idea is we have a bunch of images, a bunch of text corresponding to the images. The images are processed through a transformer image encoder to get some latent representation for images. The same for text. And then these two things are put in correlation in this matrix, where the objective is to maximize the diagonal values, okay? Because we want to maximize the similarity between the correct pairs of image and text, okay? The good things of CLIP is that it enabled zero-shot classification. So once it is trained, and it was trained on a huge quantity of data, you can use for zero-shot classification. That means what? That once it is trained, to do the classification, you just provide a list of words to the text encoder, and then one image to the image encoder, and then you measure the similarities. The similarity, the highest similarity will give you the correct label for the image, okay? So, as I said at the beginning, an important thing of foundation models is that they are trained on a huge quantity of data, and then that can be adapted to specific downstream tasks. So, we know that adapting foundation models, there are several strategies to adapt foundation models. Of course, the easiest one, the most straightforward one, is to do fine-tuning, full fine-tuning, okay? Of course, to do full fine-tuning, you need enough data just to change the parameters. One other strategy is to keep everything frozen and just change the last classification or task head. This is called linear probing. And there are also other strategies. One important strategy is VPT. Do you know VPT? Visual Prompt Tuning. So in VPT, basically, you keep everything frozen and you just learn prompts, just some specific tokens that steer the representation of the model towards the specific task. You see the fire icons there. Basically, these things here are the standard input data tokens, and you just add some additional parameters, additional tokens that are optimized to address some specific task. Another strategy, which is the most common one, is by using adapter. The techniques fall under their PEFT category. Have you heard PEFT? Parameter efficient fine-tuning techniques, and one of these is LoRa. I guess that all of you know LoRa's, where you basically learn some additional parameters in a compact way by using an encoder-decoder architecture, and you just sum those additional parameters which are optimized for your specific task to the base representation learned by the foundation models. Okay, this was a very extremely fast overview of transformers, foundation models, and how to adapt them. This, as I said, I decided to add these slides because we massively use these techniques to do our explainability work. So we know that in the last years, in the last 3-4 years, there has been a massive proliferation of foundation models. I just reported some of them, and of techniques to adapt them to specific tasks. So we are in the era where those models perform extremely good. Okay? The representation is extremely strong, but there is one problem: understanding collapsed. Okay? Because there are models with a huge quantity of parameters. This space contains is like a billion, in the billion, we have billion of parameters, so it is a huge space. Trying to understand what our model is doing and why it is doing some specific, or doing some specific prediction is really important. But of course, since these models have become larger and bigger, understanding what they're doing on specific cases, it is much more complex. And of course, the explainability research has been a long-standing field in the AI communities, but since most of the application of the AI methods we develop are going to be integrated in end-user applications, we need to address this problem more concretely, because we are in the era of the explainability crisis. Here there are a few examples. I reported some news where some specific AI models made wrong predictions or biased predictions. This is like one Amazon system used in the US to allow, to give access to people to specific buildings, and then they noticed that on one specific category, the performance were extremely low. This is a specific case where there is a bias, and what I will present, what we try to do in our lab is to understand what are these biases and eventually to correct them. And there is another point. I mean, explainability is not only because we are researchers and we want to create problems that do not exist in life, but these problems exist. And we know that there is a regulation in Europe about using AI. We know the AI Act, especially the Act states what? That any affected person subject to an AI-assisted decision should be able to receive meaningful information about the logic and understand the basis of the outcome. So that means, it is very clear, that means that every time you use AI systems to do some tasks, some automated tasks, you need to explain why, especially when these tasks involve people, okay? And we are at this stage, so we have very impressive models. They do a lot of things, but they can, at the moment, there are cases where they misclassify cookies for Chihuahua. In the top one, the cookie was classified as Chihuahua, and in the second one was classified as no, it was a muffin. Okay, sorry. So the point is why the model is doing this specific prediction, which features they're using, and is there any causal correlation between the decision made by the model and the data? These are the questions that we do in our research. So we know that interpretability is extremely complex because we are trying to understanding models that whose representation lie in a huge multidimensional nature. Moreover, in neural networks in general, the feature space comes from an aggregation of multiple of these high-dimensional spaces. So try to disentangle information from this space is extremely complex. But we have to do that because we have to move from what we have today, very big models that are able to provide very accurate predictions, to a model that in the future will tell why you're doing that. So I'm not only interested in say that the image is a cat with a specific probability, but I'm interested in providing the information that the image is a cat because it has all these features, and this is what we want to tend to in the near future. Here there is a taxonomy that probably you already know. I tried to group together a few explainability methods. So we can see that there are two big families of XAI methods. The post hoc methods, which basically try to explain the decisions made by a model which was already trained. And then there is the other family, which is the intrinsic model, which basically means what? That you create your model in an explainable way since the very beginning. One of the most relevant examples is the concept bottleneck models, which nowadays try to inject specific concept in the model representation. Okay? Of course, this kind of model can be applied if you have one very new problem, you start from scratch. But when you are in the case of foundation models, and I imagine that no one in this room can create a foundation model because you need a lot of computational power, a lot of data, we have to go to the post hoc methods. So those methods try to explain decision after training. And here there is this distinction between local methods and global methods. Local methods are methods that basically explain individual prediction. So you just provide one image, one specific data, you get the prediction on that data, and then you ask the model why on this specific instance you are making this prediction. The second family is the family of the global methods. So in that case, they try to explain globally how the model works. This is quite important because if you explain how globally a model works, you can add some cue on how the data, on the quality of the data you use for training. And you can indeed uncover some specific biases. So in our recent research, we mostly focus on global methods. You already know these techniques, right? Have you already heard about these techniques? This is one of the most used techniques for doing individual prediction. So the approach is to create some attribution maps by using the gradients of the model. In this case, it is just the output of the GradCam approach. I reported the reference. And the question that this kind of methods answer is, which area of an image does the model pay the most attention to? These are images taken from our recent work in the medical image domain. So the point is, in this case, we are dealing with angiography, and we predict some score for angiography just to understand if a patient has to undergo some surgical intervention. And we say, okay, the score is nice, but the medical doctor needs to know why. In this case, we were able to understand that the prediction was influenced by the presence of the stenosis, the one in the red bounding box. This was some work done at the COVID epoch. Transformers also have another way to understand what they are doing. One method to do that is through the attention rollout. Attention rollout basically takes all the attention scores within the transformer and then just does this multiplication over the layers and then multiply these attention scores by the input image in a way to highlight what are the most attended tokens in the image. Okay, this is just a very standard technique. These are all techniques to do individual prediction explanation. Okay, but the point is, okay, if I wanted to understand if my model has a bias, how can I do this by explaining individual prediction? One straightforward strategy might be, okay, I provide multiple images to the visual classifier, I create attribution maps, And then I need to aggregate these attribution maps and do some reasoning over them to get global behavior of the model. This is not always easy because attribution maps have some limitations that come from let's say, the features of the gradients within the neural network. So the idea of aggregating and analyzing single attribution maps is not viable, a viable strategy, okay, because they are not interpretable themselves. So the other strategy is to go directly for global understanding of model behavior. And one typical method was using activation maximization. The idea of activation maximization is once your model is trained, you try to optimize the input image that maximize some given output. So in a classifier, you have the last head, which is the classification heads. You just pick one head of the classification head, for instance, the dog class, and then you optimize the input parameters. So at the end, you optimize the image in a way to maximize that specific output, okay? And this is an example. This was done almost 10 years ago. You start at the beginning with a random initialization of the image, then you do this gradient optimization, and you come up with images like this one, even better than this one. These are examples reported in the paper trying to explain some specific classes. It was used for quite a while, but the problem is in this case that even though they optimize and they maximize some specific output, at the end, when you have to understand these things, they are not easily to understand because they generated images which do not exist. So that's one of the limitations. So they are extremely complex to interpret. Following the idea of activation maximization, there were, Nguyen specifically, used some GANs to synthesize images that maximize some specific neurons. Okay? Rather than starting from only random pixels and then trying to optimize the random pixels, they used a GAN. You know a GAN, right? Generative Adversarial Network. So you start, the idea was start to optimize the latent space of the GAN in a way to generate images that maximize some specific output. And you can see that the quality of generated image was quite way better than the ones we saw in the previous slide. And each image, generated image, should explain some specific decision of the model. And you can see on the rows the different models and the explanation for those models. Of course, one limitation of this approach is that the granularity of the explanations is constrained by the data space of the GANs. Basically, it's constrained by the data distribution used to train the GAN. Okay, if some specific data or some specific data points are not included in the latent space of the GAN, you are not able to explain that specific class. I can do just an example. You want to explain why a classifier is predicting a B, okay? And then, for instance, this is an example we will see later. And then all of the images used for training the classifier contain flowers, okay? So one possible bias is that the model says there is a B because there is a flower. And let's suppose that you use a GAN and the GAN doesn't have the flower concept because in the training data for the GAN, the flowers did not exist. So in that case, these kind of methods cannot explain that specific bias because the GANs may miss the concepts that in a way can explain some specific decision. Okay, this was the general architecture, and this is something that it is important to, for understanding the rest of the presentation. The idea is that this is the last layer, the classification heads. You pick up one classification head, and then you optimize what? The input space. In the input space, there is a deep generative network, and the input space in a GAN is the latent space, the latent space as input of the model. So you just try to identify the points in this latent space that in a way maximize the output. Okay, so I think I repeated this slide twice. Anyway, the problem here was, okay, these methods were quite good, but of course they didn't gain much momentum because the quality of generative models at the time being was not so high, even though GANs were quite good in generating synthetic images. And also the other point is that given using these images, at the end it is very hard to understand what the model is doing for making prediction. In other words, it is very hard by looking at this image to explain why globally what the model is doing, what the data used for training the model was formed. So, and this leads us to the third part of my presentation. So, from visual to text explanations, because the idea is that those images, okay, were okay, you can just check all these images, try to understand, to get some understanding on what the model is doing, but the most natural way for humans to understand concepts is through text, okay? And this is the idea that what we want to do. We want to explain, in the past, what we were trying to do is to explain some signals that in the case of classifier were images, but we are not explaining the reasoning. So we don't know the reasoning the model does to make some specific prediction. So the first work we did to perform this global understanding of the models is the approach you see here, which is called the diff explainer. Okay? In diff explainer, we try to follow the activation maximization strategy. And the idea is to optimize text prompts to steer visual generation towards maximizing neurons. So this part is very similar to activation maximization because we follow that specific strategy. What we are trying to do is to optimize the prompts. That's why I presented the different strategies for adapting foundation models, because the strategy is more or less that one. So let's see what we do in practice. So this is our classifier, and the classifier is frozen because we want to understand globally what the classifier is doing. Okay? We start from the output, as in the activation maximization strategy I presented earlier, and we go back. You see here that we have this LDM. You know LDM? What LDM is? Latent diffusion model. Have you heard this word? Have you ever heard? DALL-E, for instance, is a latent diffusion model. It's a generative models to create images conditioned by, for instance, text. So in between we have these latent diffusion models, and then which can be conditioned from by some text. And then what we do, we optimize prompts in input rather than creating the images. So the strategy is a bit different. We leverage these huge foundation models and we steer the generation of these foundation models in a way to maximize the output of our model. Okay? So you see just the difference here. This is the difference between the Guyen approach and our approach. And for instance, it is quite interesting. In the case of B class, for the ResNet 50, the image that maximizes the output for the B class contains only flowers. This can set an alarm. So probably the ResNet 50 was trained with images, with B images where there were mainly flowers. So at the end, the model learned only flowers. This is another case, for instance, of a bias that we found out with diff explainer. The class is flagpole, and at the end, the image that maximizes that class is an image of a flag of the United States flag. This is double bias in this case. But optimizing the prompt on the text space allows us also to do, let's say, finer analysis. You see here, for instance, in the previous case, the prompt that we were optimizing was structured in this way. A picture of prompt V, and V was optimized, okay? And we got this kind of images. But we can, let's say, steer the representation in the text space in a more focused way. For instance, in this case, we optimized a texture of B, where B is the prompt we are going to optimize, where the pipeline is optimized. And you can see that in that specific case, for that specific classifier, these are the texture for which the model is more sensitive. Okay? Of course, this provides us some additional information about our model. So in the case of B, again, you see that the most important texture, or better, the texture that maximizes the specific class doesn't contain any B structure in any form. In the case of dog sled, there is some snow. In the case of strawberry, there is a texture which resembles strawberries. Okay? We can do also for the shape, and we can see that in this case, there is something which is working. In this case, maybe not, because the dog sleds, there is only snow. Even for shape and for texture, there are only snow information. For the B class, we are not even able to create some shape which makes sense. This was a clear indication that in ResNet 50, the B class was completely biased. Okay? So the text at the end enables explaining with granularity up to the low-level features in terms of texture and shapes. Here you can see some results that we obtained by using Diff Explainer, because it improved bias discovery at the feature level. This was done for different classes and also for different neural features. So we know that the neural features are the features at the previous layer, at the layer before the classification one, the last layer. So if you move one layer back, you have what are the main concepts that the network is using to make some specific prediction. Here, for instance, for the class Marmot, when we generate the images maximizing these neural features, the top 5 most important neural features, for instance, we see that one feature maybe encodes some texture about the marmot, some other feature, something related to the background, because of course the background is really important. The problem is that if you use only the background to make classification, there is a bias. But to make a classification of a concept, you also need background. And you can see that in this case, we were able to understand different set of features. But the limitation of this method is that the explanations are still in the visual space. So at the end, even though we were able to generate these images by optimizing in the text space, the words we obtained here at the end, when the optimization was done, the words that we obtained replacing the B prompt was without any significant meaning. So we couldn't use those words. What we used was the images, the optimized image to explain some specific concept. Okay? So still we are in the visual space. So this led us, what if we really want to understand and explain the global behavior of a visual classifier in the text space? And this led us to let's say, the work after the Diff Explainer, which is Dexter. Dexter was published last year in NeurIPS. And the key question was, again, is it possible to explain a visual classifier decision-making process within text? So we start from visual classifier. We want to investigate model reasoning for one specific class. And we want to optimize in the text space. And we want to obtain this time some textual explanation for the visual classification behavior. And this is the Dexter optimization process. How Dexter works. This is the whole pipeline of Dexter. You see that, again, the strategy is always the activation maximization strategy. So the point is we want to generate the text that, in a way, when it is provided to a generative models, generate one image that maximizes one specific class. So you just start from here, for instance, B prediction, and then we move back until we optimize this text. And we still use the soft prompt, the prompt learning strategy, the one I presented at the beginning. So we optimize, we find the best parameters in the soft prompt there that conditions BERT. BERT generate some sentence. This sentence is passed to Stable Diffusion. Stable Diffusion generates one image. This image is passed to the classifier, and then we measure what are the confidence, the prediction confidence for the model. Of course, this is a very long pipeline. There were many challenges that I just reported here. The most important one was the vanishing gradient. So in that case, since there are many different layers and they are extremely deep, when you get some gradient and then you go back, we got, at the end, we were not able to optimize the soft prompts. Another limitation was that we used BERT. You know BERT, right? BERT is this model that is trained in using masked autoencoding, okay? Because the idea was we don't want just to optimize some space. We want some text. We want to create sentences. So to create sentences, we needed a model trained using masked autoencoding, which is BERT, okay? So at the end, you have a sentence, and you want to generate the next word. This was the strategy. Of course, the output of BERT is discrete, so we needed something to make everything differentiable. And the other point is that BERT and latent diffusion model uses different dictionaries. So we had to match these two dictionaries. As you can see here, there are basically two pipelines. There is the text pipeline, which is the one until here, and the image pipeline, which is the bottom pipeline. So this is what there is inside the text pipeline. We used the Gumbel softmax to make the output, the discrete output of BERT differentiable. And then we used some specific mapping matrix between the BERT dictionary and the latent and the stable diffusion dictionary. That means what? The problem is that with BERT, words are encoded with some specific values. In latent diffusion, the same words have different representation. So the idea was try to match this representation. And we had to do this necessarily because otherwise we were not able to create meaningful images in the image pipeline. In the image generation, at the end, once the text pipeline predicts the words, we just simply use the strategy we saw earlier. Okay? Once the soft prompt is optimized, we can get some predictions on the visual classifier, but we can do some reasoning on the images by using the text there. And this allows us to do this textual reasoning, as you see in this slide here. Okay, here you can see some results we found out with Dexter. For instance, we investigated large models, very common models, and you can notice that for the Tiger class, BIT, ResNet 50, and robust ResNet 50 do not contain any bias because the image that maximizes that class contains a tiger. For instead, the Jeep class, you see that BIT and the robust ResNet, they both contain Jeeps, but the ResNet 50 doesn't contain any Jeep. So this is an indication that ResNet 50 struggle with the Jeep classes, and also we did this also for other classes. By using this strategy, we were also able to do slice discovery and the bias. You know what is the slice discovery problem? Slice discovery is to find in the dataset specific slices, sequence of images or images that introduce some bias in the representation. One of the dataset used is the waterbirds dataset, where during training there are a waterbird image only in water scenario, and then in the test set you have waterbird images also on ground. So in that case you just you are injecting the bias in the training data. So you want to understand if the model is able to remove that bias and to use the core features for classification. So the slice discovery is a quite common problem in computer vision. The point, again, is to identify some specific slices in the training data. So we want to understand models, but we want to understand not only why a decision is done, but what is the causal, or better, the causal correlation with the training data. So you are doing wrong classification on B because the training data contains only flower images, or because there is a large portion of the data containing only flower images. What interesting things is that, of course, Dexter was almost on par or even better than competitors. But one important thing is that in Dexter we do not use either data or ground truth, while competitors use or data or ground truth or both to do this slice discovery and the biasing. Another example, just to show that Dexter works quite well, we artificially created a dataset for doing edge prediction. Okay, and we did two instances of this dataset. One where 70% of images were of male subjects, and 30% were of female subjects, and the other one completely balanced. When we passed this, we trained the model on this dataset, and we passed the trained model to Dexter. Here you can see the text explanation obtained through Dexter. In one case, it clearly states that there is a bias. You see, the slight overrepresentation of male subjects in the caption could suggest a bias in the training data. So it was able to understand and to derive that textual representation by using only the model without accessing anything more. In this case, instead, the model is, Dexter is explaining what the model does, and it states that there is no bias. Of course, this was, let's say, a confirm that Dexter was doing right. Okay, so the pipeline, the timeline of the presentation is that we started from activation maximization. We improved activation maximization with diff explainer by just using the, let's say, prompt tuning strategies. And then we moved to Dexter, where the optimization was done in the text space, and this allowed us to provide text explanations of visual classifier. So, as I said at the beginning, okay, this is quite good. I mean, explaining globally the behavior of a model through text is really much more interpretable than seeing images and trying to understand, to uncover explanation from images. But the point is, what if we don't have access to the model weights? I mean, as I said at the beginning, we are going to use AI models massively also in our mobile phone, but in many applications. And what we do, we are going to use, for instance, API service, including AI. So you don't have access to the model parameters. All the methods we have seen so far, they foresee accessing the weights because they use gradients. So we basically try to optimize the input space or the soft prompt by applying the backpropagation at the end. So for those, you need the access to the weights. So we investigated also this problem. Okay, the case where we do not have access to the model parameters. And this is the one we call the real black box problem, because you have to uncover the behavior of a model, but without but only using the predictions of that model. So this is the problem. Again, investigate visual classifier reasoning without accessing its weight. These are the models we have seen so far: activation maximization, the GAN, and the two models I presented, done by the people in my group. But when you don't have access to the parameter weights, the real black box case, these methods cannot be used anymore because they are based on backpropagation. This is the one we call dissection strategies. So we want to understand what the model is doing using only a prediction. So the objective is to maximize the activation of a visual classifier for a given class by working only with text. We want to do only text optimization without using backpropagation. How can we do that? The point is, what we can do is, we have our stable diffusion, our generative model, and we know that we can condition the image generation through some sentences, okay? Of course, we want to find the sentence that maximizes the output of the classifier. One idea is just, it is not feasible to test multiple prompts in that case. Of course, we need some signal to steer, or better, to optimize the text prompt to the model. And we want to do this without accessing the model parameters. This is what we do in this new work, which is Unbox. We use some specific technique which was published, I think, 2 or 3 years ago, which is text grad. You know text grad? Have you ever heard about text grad? So rather than using backpropagation, so forget about backpropagation, because in this case cannot be used, what you can do is to optimize in the text space. That means what? That at the end, every step of the optimization doesn't produce new parameters, but produces new text that you can use to, in our case, to explain the model. And this is done by using what? AI agents, so that are specific instances of LLM models, of large language models. So the problem is, again, we want to discover one specific class, which is the tiger class. We start from some input prompt, the PT prompt, random initialization of this prompt. The prompt is passed to a generative models. We generate an image, of course, and we pass this image to the model, okay? The model is completely black. We don't have any access. We have only access to the prediction values, these SST, which are the predictions for the model. Then we start reasoning on these predictions. How? We basically use two terms, two concepts. The one we call semantic guidance and the optimization context. In the semantic guidance, we just do what? We see if the confidence has improved, and we see if it is necessary to do some micro refinement. And here there are 3 agents. So this agent at the end, the first agent, will see, okay, this is the optimization context, all the prompts that have been used so far. What are the predictions for those concepts? Then we provide also to this agent the semantic guidance values. This basically tells the agent, of course, the objective of this agent is to do what? Given the story, given this value, to suggest some changes to the text prompt, okay? And then this goes to the other agent that, given the prompt, the initial prompt, implement these suggestions to the prompt, and the prompt is provided again back to the input. So you don't have access to any weights. What we are asking is, given the story of the confidence, okay, we start from completely different. In the case of the tiger, we start from random text prompt, an image of a house, okay? Then, of course, when we get the image of a house and we are investigating some specific output, we say, okay, for that specific output, the confidence is really low because that output at the end doesn't encode any house, but only tigers, okay? We say, okay, the confidence is really low. If the confidence is really low, the semantic guidance say, okay, probably the image, the text prompt is completely wrong. So the confidence hasn't improved, so we need to do no micro refinement, but big refinements, because the prompt is completely wrong. And we do this several times until it converges. And we never used parameters. So this again, as I said, this was done using these text grad techniques, where we basically use agents to refine the prompts that at the end generate images that maximize one specific class. What was really nice about Unbox is that we were able to measure the semantic fidelity. That means what? Given one classifier, you have access only to the prediction, the output of these classifiers. Can you understand what each single head implements? Because if you have a model and you query this model online, you don't know what all the heads represent. They will give you one specific class. So the point is, are we able to understand what are the classes that the model is able to classify? Okay? And this is what the semantic fidelity measures. So in this case, what we do, we just measures the prompts we obtained, the text words we learned through the Unbox model, and the classes we have in our dataset. Of course, this is for evaluation. For evaluation, we used the correct classes. And you can see that Unbox was able to identify the classes of a model much better than the competitors. Again, what is really interesting that we don't need to access weights and data, just using generative models. Same time, another question is, are we able to uncover training data descriptors starting from the model without accessing the parameters? This is quite important to understand why we need to understand the text descriptors and then the image that at the end will activate most our model. Because this gives us what? An idea on the training data. I mean, if we were able to understand what are the semantic words that in a way match the one we create, we are uncovering what are the training data used for creating our models. And you can see that again, Unbox is doing quite well, a bit less than Clip Dissect, but there is one point, we never access the weights, while Clip Dissect, which is a competitor, instead uses the weights. Same things is for visual grounding. Are we able to uncover visual information from training images? So the point is, using the Unbox strategy, we want to understand what are the visual features of the training data for that model. Okay? Of course, we don't have access either, again, to the parameters and to the training data. And the Unbox was quite good also to uncover this visual information. By using an extremely black box strategy, with Unbox we were able to identify some emergent spurious feature attribution. For instance, one case is, well, let me see. Here, for instance, in the library. For the library case, all the words were classroom, class, cafeteria, textbooks, and during was another text, of course, that there might be some error. These kind of things, of word descriptions, may, let's say, give us an intuition on some spurious correlation in the training data. Okay, let's move to the last part of the talk, is toward causal understanding. So, again, we are doing global explanation. We want to do this in the text space, and we want to do this without accessing the model parameters in an extremely black box way. We want to do a step forward. We want to understand causal correlations between causal correlations. So what we want to do is we want to really understand what the model is doing by using some intervention strategy to identify some specific concepts, and most importantly, to understand the knowledge structure. Okay? The models we have seen so far have a few limitations. One is that, for instance, in the case of Unbox, we had to work with closed set reasoning. That means what? That the possible classes were closed, okay? 10 classes, 20 classes, and we know the set of classes. We don't know the exact matching between the classes and the classification heads, but we knew the classes. I mean, if you want to do explanation in a really black box, you have to assume the open set scenario. You don't know. The model can predict any class in a specific language. So the problem is that the methods we have seen so far assume a fixed vocabulary of classes. Understanding is constrained by the labels of the training dataset. The other limitation is that basically they perform explanation through correlation. So the attribution and maximization identify associations, not causes. And the third limitation is that we lack a structured global understanding of the knowledge of the model. Okay? This is quite important, and we will see why it is important. So, at the moment, what we lack is a framework that is simultaneously open set, causal, and that provide structured knowledge about the specific classifier. So we want to do understanding of a model that, of course, as I write here, requires much more than describing it. So it requires intervening and structuring its reasoning. And this is what we do with Occam. Occam is this open set causal concept and explanation and ontology induction for black box visual models. We call it Occam. You know the Occam razor? Okay? Have you ever heard about the Occam razor? That's why it's called Occam. So the strategy, since we are talking about the razor, at the end is just try to cut concept in the image and see how the confidence of a classifier changes. Okay? Occam works in the open set scenario, so the concepts and the classes are not predefined. They are extracted through a pre-trained multimodal language model. It can be adapted to each image and context. In Occam, we perform causal reasoning through interventions, so the concepts are removed from the image, and then the impact of removing concepts is measured through prediction change. Okay? And this, in a way, identify this decision critical evidence. And then finally, since we do this for many, many examples, what we can do is we can aggregate these causal effects across images, and we can build a concept level representation that at the end will enable global reasoning. So at the end we create an ontology starting from those images. And this is what basically we do with Occam. So the strategy of Occam is propose, ground in the image, intervene, and aggregate. What we do is, given one specific class, whatever, we ask a foundation model, okay, what are the main concepts describing that class, okay? And we receive these terms here, like in the case of this bird here, we have eye, beak, feathers, macaw, and so on and so forth, okay? Then we use another foundation model, a segmentation foundation model, and we ask to segmentate in the image those concepts, okay? The eye, the beak, and so on and so forth. And the first one is the proposed phase. The second phase, the one of segmentation model, is the ground step. And then we have the intervene step, where we basically remove those concepts. So basically we do some in-painting strategy here, and we remove concepts. Here we remove the eye. You see there is the bird without an eye. Here we remove the beak here. And we send these images to the classifier, okay? Even in this case, we don't have access to the classifier, and then we measure how the confidence of the model changes, okay? And we do this for many, many concepts and for many, many images. So at the end, what we obtain is many instances of representation, or instances of concepts within specific classes. And what we do is we aggregate all these instances and we create an ontology based on many, many examples. And finally, what we do is we support the reasoning using this ontology.
Sorry, one question. Do you apply any concept in different iterations, or do you extract the concept only in a first?
We have both. So we start from these things here, and then we have another strategy I didn't report, that given this image we use attribution maps just to extract some low-level features, but in a second iteration. At the concept level there are no iterations. So we first do concept removal, and then once we remove the concept, like in this case, we just do what? We do some attribution here, attribution map using again TextGrad because we don't have access to the models, and we hide the most significant part, even when we are dealing with some concept features, some low-level features, sorry. Okay, I was here, so at this point, then we do the ontology reasoning. So at the end, what we do is, for some specific classes, we generate some images, and then for each image, we know what is the drop in confidence when we remove the head, when we change the scale, when we remove the legs, and so on and so forth. So these are specific ontology instances. Okay, they're not ontology instances. They are, let's say, we can say some concept level representation per image. Okay.
Just a question.
Yeah. No, we create different instances, so every time we start from an image, we do the strategy I presented earlier, so, which means I remove concepts, and then see how the prediction change, okay? For this image, I create one concept level representation, some description, a level description, in this form. For this image, I see that if I remove that, the drop in confidence is 0.4. If I remove legs, is 0.3, okay? For each image. I do for many images, and then using all these instances, I ask a foundation model, a language model, given these instances, create an ontology which basically that at the end may generate these specific instances. So we can support this emergent ontology. This is, for instance, the ontology we were able to create and that emerged by using the Occam on ImageNet. Okay? So at the end, we created this ontology. So the understanding in this case, since we are grounding the knowledge in an ontology, becomes structured and queryable. Here you can see some results about concept contribution results and localization. So just to see if the model is able to localize some specific concept in an image. But what it is really more important is this structured reasoning. So what we did is, okay, we used some specific language model, and given the image, we generated different types of description. Standard text description structured in JSON, and the ontology I was mentioning earlier. Okay? And then we grounded the language model with these three descriptions, and we asked, okay, multiple foundation models, okay, generate the description for the image by using this ontology. This is what we did in this case. Okay? Generate a description of the decision process for a specific class using only the output JSON of the model. And the first case is generate the description of the model using the DEX strategy, only free text. Okay? Is what we did. And then we asked humans to evaluate the description of the problem in the three cases. Okay? So just to make it clearer, we started from images, we applied the Occam strategy. Okay? With the Occam strategy, at the end, for all the classes, we can create an ontology. Okay? This is one output. We did another procedure. Rather than creating the ontology, the formal ontology, we say, okay, do structure the knowledge using a JSON without any ontology structure. And this was the second approach. And the first approach is, okay, given the Occam strategy, generate free text that in a way describe the change, the prediction change when we remove concepts. Okay? So we structure the knowledge in three ways: free text, JSON, which is more structured than free text, and ontology. Okay? And then we said a language model, with a sort of RAG we did in this case. Say, okay, provide explanation by using this ontology. This was this column here. Provide explanation using only the JSON, provide explanation using only the free text. And we asked the humans to evaluate the descriptions, the explanations done by the model in the three cases. And you can see, this was done on Amazon Mechanical Turk, that using the ontology led to much more intuitive explanations and better received by humans. Okay? So I think we can go to the conclusions of this talk. So what we are trying to do is, and what we have to do, when I say we have to do, is as a community. We have to move from performance to understanding. We know that we can build powerful models and we can explain their outputs, but we need to understand what these models do, and this requires intervention and requires structure. This is at least what the Occam work tells us. Okay? We need to remove concept and try to understand how the models change their prediction when concepts are removed, and we need to structure the knowledge in a way, and we did this through an ontology. And this means what? That to open the black box, we need to change our explainability paradigm. We need to move from features to concepts. And this is what the community tells us. Also, the concept bottleneck models I was mentioning earlier clearly states, do not work with features, with lower level features, but work with concept. And this is what we did in Occam. We need to move from explainable signals, explainable images, to causes, and we need to change the way we structure our outputs. So we need to give some specific structure to the knowledge derived from our models. I think I'm done. Thank you.
Comment, question? One, two? Okay.
Okay, first of all, thank you very much for the talk. Really interesting. And I have a question about the last proposal.
The Occam, you mean?
Yeah, about Occam, and especially about the causal part, and how and why do you state causality? Because I feel like what you do here, it's you modify the input in terms of the features, in terms of like an intervention will be, and see what is the effect on the model.
Yeah, this is causality.
Okay, but what I will say it's these models, especially deep networks, are not linear, are also well known for having weird behaviors. For example, adversarial examples, which could be like looks noise, and the models may think that it looks like this. So how do you interpret this?
Well, I mean, I see your point. I mean, if you do intervention at the feature level, I mean, it is, let's say, a bit far-fetched to say causality. But what we do is we remove concepts. Removing concepts that have some semantics somehow implies some causality, because you can see how the model reacts to removing some high-level concepts. That's why we call it causality. I didn't get the part about the adversarial attack, actually.
Okay, so my question will be you always test for in-domain data for mechanisms that are in-domain. Like you never test whether this causal implication will generalize to an out-of-distribution sample.
Well, in this case, there is no in-domain because we don't know anything about the model. Completely. It is completely black box. So we don't know anything about how the model was trained.
Okay.
And what we did, of course, when you, for instance, if you select here classifier, for instance, and then you use generative models, the distribution is completely different. So you are in the case of out of distribution. Since we do this explanation on real samples, but also on synthetic samples, we are in a way dealing with the out of distribution problem.
Okay, and thank you very much for the talk. Really interesting and enriching.
Yeah, thank you very much.
I also thank you for the speech. I was wondering, when we do a strategy like this, so we are removing the important concepts, but we also remove the background. Now, in real life, we use the background, for example, to classify. For example, the snow leopard is typical from Nepal mountains. So when we saw a leopard and a snow leopard, to classify them, we also use the background information.
Yeah, I totally agree. I mean,
shouldn't we add a background concept?
There is also background concept added. I mean, I totally agree, because when we do as a humans classification, we use an holistic approach. We don't use only like core features of the objects, but we see also the environment where these objects generally. But what we do here is we remove concepts, core concepts, but also let's say background concepts, because it is really important, especially when we are doing fine-grained recognition. As you said, if you distinguish two different leopards, probably use more the background than the core features. So, but this is something that we do, and the results in the paper also include one dataset, one fine-grained recognition dataset. Okay.
Just a small curiosity. In one of the last slides, you put from performance to understanding. Is this one? For me, it's not understanding; it's interpretation. Just to clarify, because understanding is more the mental process to read.
I agree. That's why I agree. That's why we call understanding. We call understanding because we are moving towards structuring the knowledge. And if you structure the knowledge, you are going towards that process. But I agree, that is a bit stretched as a term. Yeah.
But congratulations, excellent talk.
Can you go again to the OCAN slide, please? I'm curious about the concept generation, because you use an LLM, right? A foundational model. So to extract the concept.
To extract the concept.
Yes. I'm not sure, have you tried, for example, more this descriptive concept as, I don't know, instead of legs, short legs or long legs?
Yeah, we're also using objectives.
Yes, because I think that's the point, because the concept phase is a difficult phase to find the concept in the concept bottleneck. So now you are using an LLM, it could be useful.
Yeah, what we do is we extract these concepts here, and then we combine with the several objectives.
A predefined adjective.
Yeah, just with a list of possible objectives. The problem, the main limitation here that you have is in the segmentation model. Okay. Because the segmentation model might not be able to extract some specific, like, let's say, very long beak, for instance. The concept of very long in the segmentation foundation model, which is more at the low level, feature, working more on low-level features, might be more complex. But what we do is just we combine those concepts.
Okay, because I was thinking more for the causal part that we are discussing a lot about that. It would be more interesting to talk about the adjectives of the concept that.
Yeah, I think I'm not sure, but I remember that in the descriptions, so we add also these things. That's why we talk about causality, because we also include not only concepts, but the way these concepts are combined.
Okay, that's all. Thank you for the talk. I think it was so interesting for people not working in visual as me, so thank you.
Okay, I'm happy. There is one question there.
Ivan?
Thanks for the talk. It was a really nice talk. I'm not so working on explainability, and this is like my area. What I want to reach are actually most of your papers. So nice. But my question is more related with the power of your models that you are using to explain. I mean, let's say I have a ResNet 15 or something, or even VIT, and we are using BERT, we are using CLIP, we are using several, like they are so big compared to the model that we are about to audit at the end or extract explanations. I see the point that right now what we are doing is auditing and checking the concepts, the ontology and so on. But in terms of production, like once we discover that our model is the biased and our model take the concepts, is it easy or low? It takes not too much to take or not too much power, like all of those models to extract the explanation from the output of the small model that we want to explain.
I think I missed some part.
Okay, sorry. What we are doing here at the end is auditing, extracting the concepts, the ontology, and so on.
Okay.
And we are using like CLIP, BERT, all of those
models,
stuff. But in terms of after we extract those concepts and so on, is it easy not to use the whole model, the whole BERT, because at the end it feels for me like we are using too much power to explain a small.
Yeah, but the point. Now I see your point. But the point is that to do this explanation, you need to have a very large knowledge. That's we use the foundation models. Then you can explain even simpler model like ResNet 50 or ResNet 18. But at least to understand, for instance, if one specific concept is not included in ResNet 50, you need someone that tells you have to investigate that specific concept. So you can see these large foundation models like your knowledge base to start for the explanation. But then in the production stage, you do explanation of only the simple models.
So it's just a follow-up to that question, and it's asking if you are treating these foundation models as your knowledge base, then you always need a model that knows more than yours to be able to explain it.
No, more than?
More than yours. Like you need these models, like these foundation models, to capture more knowledge than your small, like in this case, your ResNet.
I totally agree. I mean, if you wanted to explain a larger model, you would need even larger model. Yeah.
Okay.
Yeah, I totally agree on this. Yeah.
Yes, that.
Yeah, and another problem, because of course it is not like everything beautiful. There are many issues because we use a lot of foundation models, but foundation models have their own biases. So we have to control the biases of the foundation models when we do explanation of another approach, and it's something that we are working on.
Not for the talk.
Thank you, Concetto. I'm wondering, because we are doing similar thing with extracting the ontology, but for fine-grained distinction of different classes that are very similar. For instance, a flower has 5 petals, and another class, the only difference is the texture, or that it has 7 petals, or things like that. Like, how do we make sure with the human that is not an expert on biology or some very subtle nuances to evaluate that the extracted ontology has also the right edges, the right semantics, like ontology rich level kind of
if the ontology is right.
Yeah, exactly. Like the human normally doesn't know or is not expert on.
Yeah, I mean, but this is something that we asked ourselves. Of course, we did this for, let's say, general computer vision problem in the very simple images, the one you can find so in ImageNet. But when you go for domain-specific applications, the only things you can do is to compare, to ground the emergent ontology with some existing ontologies on that field. For instance, this is something that we are working on. There are these, in Sicily there are many types of pear, like the fruit, many types, and the visual changes are very tiny. I mean, it is in the tree, and we have an ontology. I mean, the people working in the field, they created an ontology. So we are collecting now the data. We will. The objective is to make to apply Occam to create the emergent ontology, and then what you have to do is only try to see if the two ontologies in a way match. But in the case of natural images, as we did in Occam, the ontology, the emergent ontology, we were able to extract, merged the WordNet ontology. This is quite interesting because ImageNet is built using WordNet, and by using only the data, we were able to get to that point in a very black box way.
Okay, thank you.
Any other question, comment? Thank you very much.
Thank you.